Okay, moving along. Now we're going to talk about implicit differentiation. So usually, implicit differentiation requires us to have a function y be in terms of a independent variable x. So we could technically explicitly derive this equation by isolating for y, right? So we'll have to do, so let's write out the original equation first. So this would be x squared minus y squared equals 25, right? So we could explicitly derive this. Explicit differentiation. We can explicitly differentiate this by isolating for y, right? So we can say we move everything to the left except for y. So we'll have 25 minus x squared. So we'll have x squared minus 25. Okay, and then we square root everything. And we could explicitly derive like this, right? So we can say, okay, so we're going to do a dy of dx here. So implicit differentiation does not require us to isolate for y squared. And it's very useful for functions that we cannot explicitly derive, or we cannot find the function y in terms of x only. So implicit differentiation suggests that we just derive as is, and we derive everything in terms of x, okay? So implicit differentiation. It suggests that we just derive, sorry, that was that. It suggests that we just derive in terms of like this. So we do d of dx of x squared minus y squared, and we do d of dx of 25, okay? So if we were to explicitly derive this, this is what we'll get, okay? So this is our difference quotient, or difference differentiation, so we can split it up. So this would be d of dx x squared minus d of dx y squared, and this just equals 0, okay? All right, so derivative of x squared is just 2x, and derivative of this would be a chain rule, right? So there's an outside function and there's an inside function, right? So the outside function is going to be 2y, and our inside function, we don't know what the derivative is in terms of x solely, so all we're going to write is y prime, or dy of dx, okay? So we're just going to say derivative of y is just dy dx, we just don't know what it is, and this is equal to 0. We're going to isolate for dy dx now, okay? So dy dx equals 2x divided by negative 2y, okay? And we get x over y as our final answer, okay? So you notice here that our derivative in the end is in terms of both variables here, okay? So you can see here that we have x and y. Compared to explicit differentiation, if we were to derive this, right, we would have a chain rule here, so it'll be 1 over 2 x squared minus 25 negative half, and then derivative of the inside is just 2x, which would equal to x divided by the square roots of x squared minus 25, okay? So that is our explicit differentiation, and we see here that our function here is in terms of only x, okay? So we have derived in two different ways, but our derivative of dy dx is in terms of x and y through implicit differentiation, and our explicit differentiation is only in terms of x. In this case, since our function is actually easily isolated for y, we can sub back in y here, right? So if we were to say sub in y, we can get dy over dx equals x divided by, y is here, right? Y equals root of x squared minus 25. root of x squared minus 25. And we get the same thing. So we know that we implicitly differentiated correctly. Now, this was a very simple, I guess, example of implicit differentiation. And you can also do it explicitly, right? But there are some functions out there that you cannot explicitly differentiate easily. So implicit differentiation is actually the preferred method of finding the derivative, okay? So the junior tutor, they implicitly derived. They suggested that we use a power rule, and then they used the power rule and the chain rule here, and they came up with the same solution as we did. So this solution is correct.